Assalamualaikum warahmatullahi wabarakatuh. In this video, we will be presenting about crystalline solids for subject CHM361. Here are the objectives for this video presentation. First, to explain what crystalline solids are, to differentiate crystalline and amorphous solids, to describe types of crystalline solids, and last, to understand crystal structures and defects. First of all, what is solid? A solid is a state of matter in which the atoms, molecules or ions are arranged very closely together in a regular and orderly pattern. In solids, the particles are held in fixed positions and can only vibrate or rotate rather than move freely. This rigid arrangement is due to the very strong attractive forces between the particles which prevent them from moving without disrupting the entire structure. As a result, solids have a definite shape that does not depend on the shape of their container.
So we move on to crystalline solid. What are crystalline solids? Crystalline solids is a material with constituent arranged in a highly ordered, repeating three-dimensional lattice extending in all directions. The key characteristic of crystalline solid is that it has a long-range order, which means that the arrangement of the particles repeat periodically over the entire crystal. It also has a definite melting point, which it melts at a specific temperature. And last one is anisotropy, which it has some physical properties like refractive index and thermal conductivity that vary with direction. And we got the examples such as salt, diamond, and quartz.
This table summarizes the four main types of crystalline solids based on their particles, bonding properties, and examples. Metallic crystalline solids consist of metal atoms held together by metallic bonding, and the presence of delocalized electrons allows them to conduct heat and electricity, such as copper and iron. Ionic crystalline solids are made up of positive and negative ions held by strong electrostatic forces, giving them high melting points and making them hard but brittle. For example, sodium chloride and calcium chloride. Covalent network solids are formed when atoms are bonded together by strong covalent bonds in a 3D network. As a result, these solids are extremely hard and have a very high melting point. Diamond and graphite are a common example. Molecular crystalline solids are composed of molecules held together by weak intermolecular forces such as van der Waals forces or hydrogen bonding. Therefore, these solids usually have low melting points and are relatively soft. Examples include ice and...
There are three primary types of cubic crystal structures. The first is the simple cubic structure, where atoms are located only at the 8 corners of the cube, resulting in a coordination number of 6. An example of this structure is polonium. The second type is the body-centered cubic structure BCC, characterized by atoms at the 8 corners and 1 additional atoms at the center of the cube. This arrangement results in a coordination number of 8 and is found in metals such as iron and sodium. The third type is the face-centered cubic structure FCC, which is the most densely packed. In this structure, atoms are positioned at the 8 corners and at the center of each face, resulting in a coordination number of 12. Examples include copper, aluminium, gold, and silver. I will explain on the fundamental building blocks of materials by exploring crystal structures. To understand how solids are formed, it is essential to first define several key terms. A unit cell is the smallest repeating unit of a crystal lattice that forms the entire crystal structure when repeated in all directions. Within this cell, lattice points represent the fixed position where atoms, ions, or molecules are located. Additionally, the coordination numbers serve as an indicator of how closely atoms are packed, representing the total number of nearest neighboring atoms surrounding a given. To determine the actual number of particles in a unit cell, the contribution of each particle must be calculated based on its position. Particles at the corner are shared by 8 unit cells, thus contributing only 1/8 of an atom to a single cell. particles located on an edge are shared by 4 unit cells, providing a 1/4 contribution. Those situated on a face are shared by 2 unit cells, contributing 1/2 of an atom. Finally, a particle at the center is not shared and contributes 1 full atom to the unit cell. These values are essential for calculating the total atomic occupancy within different crystallities.
Crystalline solid. Ionic solids are very hard because ions are held by strong electrostatic force, but they are brittle as light charge repel when layer shift. This causes strong electrostatic repulsion, making the crystal shatter along a plane rather than bend. Ionic solids do not conduct electricity in their solid state. However, when melted or dissolved in water, the ions become mobile. In the molten state, heating allows the ion to move freely, enabling conductivity. In an aqueous solution, the ions separate and are surrounded by water molecules, allowing them to carry current. Ionic solids have high melting and boiling point because strong electrostatic attraction between fully charged ions require much energy to break this force. Metallic solids are generally hard but also malleable and ductile. The layers of metal ions can slide over one another without breaking the structure because the delocalized sea of electrons continue to hold the lattice together. Metals are excellent electrical conductors in both solid and liquid state because delocalized electrons move freely through the lattice. Metals have high melting and boiling point due to strong metallic bond between positive metal ions and the sea of delocalized electrons, especially in transition metals. These solids are generally soft and easily scratched because the molecules are held together by weak intermolecular force, making the structure less rigid. Molecular solids do not conduct electricity because they consist of neutral molecules with no free ions or delocalized electrons. The electrons are localized within covalent bonds, preventing the movement of charge, so the solids act as electrical insulators. Molecular solids have low melting and boiling point because only weak intermolecular force hold the molecules together. So, little energy is required to overcome this force and change their physical state. Covalent solids are very hard due to strong three-dimensional covalent bonds throughout the structure. However, they are brittle and can shatter when stressed because deforming the lattice requires breaking many strong bonds. Covalent solids do not conduct electricity because electrons are localized in covalent bonds except graphite and graphene, which are delocalized electrons, allowing them to conduct electricity. Covalent solids have very high melting and boiling point because a large amount of energy is required to break this strong covalent network, which is why substances like diamond and silicon dioxide are extremely thermally stable.
Crystal defect. Crystal defect is irregularity in the arrangement of constituent particles in a solid. The ideal crystal does not exist. There is 2 crystal defects. The first one is stoichiometric defect, which is irregularities or deviation from ideal arrangement, and the second one is non-stoichiometric defect, which composition deviates from ideal ratio. There is 4 types of stoichiometric defect. The first one is vacancy defect. It got missing atom or ion that causes the density to decrease. And then the second one is interstitial defect. It has an extra atom in the gap that increases the density. And the third one is Schottky defect. One of its paired cation and anion is missing. It decreases the density and the influence of conductivity. And the last one is Frankel defect. A cation displays to an interstitial site that causes the density and electrical neutrality to not change. There's 2 non-stoichiometric defects. The first one is metal excess defect. An anion is vacant and it was filled by an electron. It is responsible for imparting color to the crystal. The second one is metal deficiency defect. A cation is vacant and the other cation changes the charge. It occurs in compound where the same metal can exhibit variable valency.
This slide shows the real-life applications of different types of solid, which are ionic solids, metallic solids, covalent network solids, and molecular solids. First, ionic solids are commonly used as electrolytes in batteries. electrolysis processes, and also in medical salines such as sodium chloride. This is because ionic compounds can conduct electricity when they are dissolved in water or in molten form. Next, metallic solids are widely used in daily life, especially in wiring, constructions, and machinery. For example, copper and aluminium are used for electrical wiring, while iron and steel are used in buildings and heavy structures. This is due to their high electrical conductivity, strength, and durability. Moving on to covalent network solids, examples include diamond, silicon, and graphite. Diamond is used in cutting tools because it is extremely hard. Silicon is important in semiconductors and electronic devices, and graphite is used as electrodes and lubricants. These applications are possible because of their strong covalent bonds. Lastly, molecular solids can be found in everyday items such as pharmaceuticals, sugar, iodine, and ice. These substances usually have low melting points and are often soluble, making them suitable for daily use, especially in food and medicine. Overall, this shows how the structure and bonding of solid directly influence their properties and practical application in real life. In conclusion, crystalline solids have a well-defined and repeating arrangement of particles which give rise to unique properties such as definite melting points, hardness, and electrical conductivity. The internal structure of crystalline solids directly influences their physical and chemical properties, which in turn determines their practical application in everyday life. Therefore, understanding crystalline solids is essential in organic chemistry as it helps in predicting material behavior and in the design of functional materials for various applications.